This conference will now be recorded.
Hello everyone. So today we will discuss first some problems and then integrated rate laws and how we can obtain those rate laws by integration, starting from rate law expression. Fine. And after that there will be some related problems. So this problem is basically based on Arrhenius equation. A certain reaction proceeds in a sequence of 3 elementary steps. So when there are 3 elementary steps in the mechanism, the corresponding rate constants are K1, K2, K3 respectively. And the observed rate constant for the reaction is expressed as K observed. That means this is overall rate constant. So K will be related to K1, K2, K3. Similarly, if we consider the energy of activation, that is observed energy of activation, it is basically the overall energy of activation. And if we consider individual energy of activation for step 1, step 2 and step 3, then this will be E1, E2, E3. We have to find out how the overall energy of activation, that is E, I'm writing simply E for simplification, it is actually E observed. E observed is related to E1, E2, E3. But what is the relationship between E observed and E1, E2, E3? That we have to find out. Because here it is mentioned, if the observed rate constant of the reaction expressed as K equal to C, K1 by K2 to the power 1 by 2 multiplied by K3. So this is the relationship between K and all these 3 Ks for 3 elementary steps. This relation is given. From this you have to find out the observed energy of activation of the reaction, how it is related to these 3 individual energy of activation. Because if you look at the options, first option it is containing E1, E2, E3. Though it is not specifically mentioned what is the meaning of E1, E2, E3, but you can understand as there are total 3 steps, 1, 2, 3. So obviously E1, E2, E3, these will be the corresponding energy of activation. Okay. In option B, we have only E1 and E3. Then in option C, E3, E1, E2, all these 3 are there. And in D also, all these energy of activation terms are present. So first we will write the relationship that is given, that is K equal to K1 by K2 to the power half, that means it is under root, multiplied by K3. Next we will take log both sides, or we can take ln, that will be better. So when we are taking ln, it will be ln k half ln k1 minus ln k2 within bracket. And as there is multiple sign, that means it will be plus ln k3. Now from Arrhenius equation we know that ln k is equal to ln A minus energy of activation divided by RT. So this equation we will put for all these k. In the left hand side it will be simply ln A minus E by RT. So this E is basically E observed, that is observed energy of activation. But for simplicity I am omitting the OBS term. If you want you can write it. Okay, so this is the energy of activation observed. Right hand side in place of ln k1, now we will write ln A minus E1 by RT. And in place of ln k2 we will write again ln A, but now there will be a negative sign before it, and negative negative cancelled, it will be E2 by RT. And in place of ln k3 we will write ln A minus E3 by RT. Now within the second bracket ln A it will be cancelled. Okay, and see in the right hand side we have ln, left hand side also we have ln. So these two will also be cancelled. And you can also take common RT from both sides. So RT will also be cancelled. So ultimately we are left with E observed, or simply E, that is equal to half minus E1 plus E2 minus E3. Now if this negative sign we are removing, obviously in the right hand side also negative sign will be exchanged. So now it is not minus E1, now it is plus E1 and minus E2, and this sign is also plus. So can you tell me it is matching with which option? Look at the options carefully. All the terms are present, E1, E2, E3. So obviously this is not correct, right? Here E1 by E2 ratio is present, but in our case there is no ratio, it is simply E2 is subtracted from E1. So it is matching with option D. Any doubt? Is it fine? Next problem. This is also energy of activation related. Here we are having two equations. Both are actually same reaction, but what is the difference? In the first case there is no catalyst. In the second reaction there is catalyst. It is same reaction, but catalyst is now present. Now as we are using catalyst, temperature is decreased from 700 to 500, because we know when we use catalyst, energy of activation decreases. And as energy of activation decreases, now low energy is sufficient. That is, even if temperature is low, it is fine. That is why here we have 500 Kelvin. But where no catalyst is present, then 700 Kelvin. It was found that energy of activation, that is EA, is decreased by 30 kilojoule per mole when it is in presence of catalyst. So we know that in presence of catalyst, energy of activation decrease. And by how, that is, what is the number by which it is decreased, that is also given, 30 kilojoule per mole. If the rate remains unchanged, then activation energy for the catalyzed reaction is, we have to find out the activation energy for the second reaction. For the first reaction, if suppose it is EA, then for the second reaction it will be EA minus 30. That is the relationship. Assume pre-exponential factor is same. That means remember Arrhenius equation, K equal to A to the power A into E to the power minus A by RT. This A just before the exponential term, that is pre-exponential term, because it is just before exponential term. So this A value will remain same in both these two equations. Okay. Here options for the energy of activation value all are given in kilojoule per mole, and this is also kilojoule per mole, so we don't have to worry about the unit conversion, right? Here K1 will be equal to K2, because it is already mentioned that rate will remain same. That means rate constant will remain same, because these two are actually same reaction. Now when rate is same in for the equation 1 and for equation 2, that is K1 is equal to K2. Now in place of K, we can write this expression, because in general from Arrhenius equation we know we can express it in this way, EA by RT. So that is why we have written for equation 1 A into E to the power minus EA1 by RT1, and in place of K2 similar expression, only difference is now temperature is T2, energy of activation is A2. These two will be cancelled. Exponential both sides. So exponential is also cancelled. Negative sign is also cancelled. Ultimately we are having this relationship between activation energy and temperature. Okay. Now EA1, that is the activation energy for reaction 1, EA2 activation energy for the reaction 2. Now the relationship between EA1 and EA2 is that EA2 is 30 kilojoule per mole amount less. So if it is so, we can write that EA2 is 30 less than EA1. That means EA1 is equal to EA2 plus 30. Now we will put this value of EA1 in this equation. So suppose this is equation number 3. So putting the value of EA1 in equation number 3, now the equation will be converted to like this type of expression. Okay. Now both side we have EA2 because EA1 is no longer present. EA2 basically the unknown term that we have to find out. In place of T1, T2, we will write the temperature values 700 per. So ultimately the value of EA2 we are getting 75 kilojoule per mole. Okay. So the activation energy for the catalyzed reaction, that is for the second equation, it is 75. That means initially the value is, it is 75. Okay. So EA1 is basically 75 plus 30. But this is not actually asked. I'm just showing here. Fast reaction 105 kilojoule and 30 amount less is the activation energy, which is for the second reaction. So correct option will be option 4. Should I discuss it once again or is it fine? Can I proceed to next question? Again, a question which is related to energy profile diagram. Okay, so in energy profile diagram we have energy in the y-axis, and in x-axis we have reaction progress. That is, as time is increasing, what will be the change in the reaction. In a hypothetical reaction, that is A to B, activation energies for forward and backward reactions are given 15 and 9 kilojoule per mole. This is for forward, this is for backward reaction respectively. Potential energy of A, that means for starting material, potential energy given 10 kilojoule per mole. From these three information, basically three values are given: activation energy, forward reaction, backward reaction, and the third information that is given, potential energy of starting material, that value is also given. So from this, we have to identify which of these option is actually correct. Okay. Threshold energy of the reaction is 25 kilojoule per mole. Potential energy of B 16 kilojoule per mole. Per mole it is not given, simply the value is given. Heat of reaction 6 kilojoule, and the reaction is endothermic in nature. So if we draw the graph from all this information, see here for forward reaction energy of activation is high. That means what type of energy profile diagram we will have? It is like this. See, this is the starting material A, and the product is B. Starting material, potential energy in the y-axis, and this is actually reaction progress. This type of graph is known as energy profile diagram. So from point A, that is, if we draw a line over energy axis, it is 10 kilojoule because that information is given here. So obviously, if this is the product line, okay, because according to the information, activation energy 15 and 9, if we draw a graph like this, This is the transition state, right? So if it is transition state, the gap between the energy A and the transition state, this gap is actually 15 kilojoule, because this is the energy of activation for the forward reaction. And from the product energy, if we take the difference with the transition state, this value is 9 kilojoule. So for this type of nature of the graph, we say that this type of reaction is known as endothermic reaction. That means this statement is true. Suppose if the graph nature is like this, A is somewhere here, that is A having more energy compared to B, and B is here. Then the nature of the graph is like this. In this case, as energy of product is lesser than A, so this amount of excess energy that will be liberated, and it will be exothermic reaction. But in our case, energy of product is higher compared to starting material. Okay, so that is why here energy will be absorbed and the nature of the reaction will be endothermic. So the last statement is correct. Next we have to find out threshold energy. Is it 25 kilojoule? Now what is threshold energy? That we have discussed in the last class. Okay, so threshold energy is basically activation energy plus potential energy. So here activation energy for the forward reaction is 15, and this gap is 10, because it is 0. So 0 to up to this distance it is 10. So this difference we know it is 15, and this difference is 10, and threshold energy is basically this total difference. So that means that threshold, sorry, it means that threshold energy will be equal to 15 plus 10. That means it is 25 kilojoule. So this statement is also correct. Okay. Next statement, potential energy of B is 16 kilojoule. So potential energy of B is basically this value. If you just extend this line, it is cutting somewhere here, right? So if it is cutting here, then this gap basically we have to find out. Let me change that. So this gap now we have to find out. Okay, and it is mentioned that it is 60. So how to find out? This gap we already know, but this gap which is mentioned by C, that we have to find out, because if you just add this gap with this one, you will get this total energy gap. So here this value is 10, and how we will get this one? It is very simple, because this distance is 15 and this distance is 9. So it is basically, that is potential energy of B, that will be equal to 10 plus 15 minus 9. That means it is 10 plus 6. Is it fine? Is it clear how we are getting this value? And the third statement, this is also correct. Third statement, heat of reaction is 6 joule. So what is heat of reaction? So heat of reaction, basically this gap, that is the gap between potential energy of A and that of between B. Okay, so here we can see, in this case B is having higher lesser energy compared to A, but in both cases it is actually the difference of product and starting material. So here product line is this and starting material is this. So this gap we have to find out, which we already know. This is nothing but 15 minus 9. So heat of reaction, which is basically present by del H, that will be equal to 15 minus 9, that is 6 kilojoule. So the third statement, that is also correct. This is actually multiple correct type. Okay. So all are correct. Is it clear? Should I repeat? this gap is del H. Okay, that is C. If we denote this gap by C, del H is equal to C. Graph related problem. Rate constant K of a reaction is measured at different temperature, and after doing so, we are having a plot here which is basically having ln K in the y-axis and 10 to the power 3 divided by T, that is temperature, in the x-axis. From this plot, we have to find out what is the activation energy for the reaction in kilojoule per mole. R is here gas constant, that is universal gas constant. The value of activation energy in kilojoule per mole, options are 2 by R, that means 2 by universal gas constant, then 1 by R, simply R, or 2R, all are having unit kilojoule per mole. Here the line is only this portion, but here if we look at this dotted part, basically if we extend this line both sides, it will be joining the y-axis at this point. That means here the value of ln K is 10 and it is cutting the x-axis at the point 5. That means here the value is 5. Okay, so from this two information we can find that here slope of this line is the value in the y-axis, that is 10, divided by the value in the x-axis, that is 5. So it is basically 2. Okay, now ln K versus 10 to the power 3 divided by T. So for this type of nature of the graph, first we will take Arrhenius equation. Okay, now ln both sides, so it will be ln K, and right hand side it is ln A minus EA by R. But if we simply consider this equation, suppose this is equation number 1, then see here we do not have any 10 to the power 3 term. So that is why if you are drawing here graph, it will be simply ln K versus 1 by T. But our graph is ln K versus 10 to the power 3 by T. So what to do? Simply multiply in the numerator and denominator 10 to the power 3. So you are adding 10 to the power 3 both in numerator and denominator. So ultimately basically you are adding nothing. It is simply 1. But we are now getting this term. Okay. Now the purpose why we are doing this is that if you compare this equation with C plus mx, so this is actually x, ln K is y, ln A is C, and this total part is slope m. That means m is equal to minus EA R into 10 to the power 3. Okay, by comparing these two equations, this is equation 2, this is equation 3, compare 2 and 3, you will get this value. Okay, now slope of the graph that we have already calculated here. Sorry, I forgot the negative sign because it is negative slope. When we are increasing temperature, basically the value of ln K is decreasing. See, when temperature is 3, the corresponding value of ln K is somewhere here. When temperature is 4, then the value is somewhere here. That means when you are increasing temperature, ln K is decreasing. That is why here it is negative slope. So if it is slope which we have obtained by comparing 2 and 3, and we have also calculated slope m is equal to minus 10 by 5, that is minus 2. Minus minus cancel. So EA will be equal to 2R 10 to the power 3 joule. But we have to express it in kilojoule per mole. So that is why ultimately this 10 to the power 3 will be removed and it will be kilojoule. So which option is correct? Is there any doubt? which is the correct option? Is it clear? This problem is related to temperature coefficient. Now this term you are seeing first time because I have not discussed it before, and this numerical I am discussing intentionally so that we can understand what is temperature coefficient and how we can calculate it. It is saying that rate of a chemical reaction increases by 1024 times when there is 100 degrees centigrade rise in temperature. What it means? It means initially if the temperature is T, and another experiment we are doing where we have increased the temperature by 1000 degree centigrade, sorry, 100 degrees centigrade. So what will happen if it is KT and if it is KT plus 100, then KT to the power, sorry, KT plus 100 divided by KT, that is 1024 times. It is the meaning of this line. So from this information we have to find out what is temperature coefficient. But we do not know what is temperature coefficient. So first we have to know what is temperature coefficient. But this information is clear from this line statement that is given in the question. So what is temperature coefficient? It is actually a ratio of rate constant of two temperature. So suppose we have two temperature T1 and T2, corresponding rate constant K2 and K1. So when this temperature is differing by 10, that means T1 is basically, sorry, T2 is basically T1 plus 10. So the difference between these two temperature is 10. So when this is the case, then the ratio of rate constant, that is K2 by K1, this will be equal to temperature coefficient. Okay. So when temperature is differing by 10, then the corresponding rate constant, if we take the ratio, then the ratio that we are getting, that is temperature coefficient. And most of the time when we increase temperature, there is increase in rate constant. So obviously here K2 is greater than K1. So temperature coefficient, this will be a whole number. Okay. So rate constant at T2, which is basically rate constant. Rate constant at T2 temperature divided by rate constant at T1 temperature, that will be equal to temperature coefficient. TC means temperature coefficient to the power del T minus 10. Now del T means what? Del T is T2 minus T1. This defines. Now when we are saying temperature coefficient, how, that is K2 and K1, suppose it is temperature coefficient. Here we have not written any power. Why it is so? Because when del T is 10, when del T is 10, basically it will be 10 divided by 10. That means what? It is simply Tc. So when temperature difference is 10, then K2 by K1 is directly equal to temperature coefficient. But it is not always necessary. Del T may not be equal to 10. It may be different. So in that case, what we will do? We will use this equation. So remember this equation: rate at any temperature T2 divided by rate at any temperature T1, that is equal to temperature coefficient to the power the difference in temperature, that is T2 minus T1, divided by 10. Okay. Here it is given 1024 times. That means using this equation, that is K2 by K1, it will be 1024. And temperature coefficient we have to find out. Here del T value is basically 100 degrees centigrade. We do not know what is the final temperature and initial temperature. We just only know what is the difference between the initial and final temperature, and that information is enough. So it is 100 divided by 10, because in our case del T is 100. Okay. Now after this, in place of 1024, you can write 2 to the power 10. Okay, because 2 to the power 10 is actually equal to 1024. Now if you are thinking why I am doing so, the reason is in the right hand side it is Tc to the power 10. So when both are having same power, basically you can compare both sides, and what it means, 2 equal to Tc. So temperature coefficient is 2. Correct option is first one. Okay, in this way we can find out temperature coefficient. Is there any doubt? In last class, we have started discussing different factors affecting the rate of reaction. So the factors that we have discussed, that is 4 to 5 factors, like nature of the reactant, then temperature, catalyst, etc. And the last point, that is the last factor which affects rate of reaction, that is actually radiation. So when we are saying radiation, it is basically electromagnetic radiation, and it is applicable only when the reaction is photochemical in nature. Photochemical in nature means this reaction occurs in presence of light. That is why we are calling it photochemical. So normal reactions, what we do is simply heat. That means we are providing thermal energy. But here it is the energy which is coming from light. Okay. So in presence of light, you can find some reactions. It is not that all reactions are possible in presence of light, but some reactions are possible. So instead of thermal energy, now we are applying electromagnetic radiation, which is also a form of energy. And as we know that when we increase temperature, rate constant, there is some change. So obviously when we are applying electromagnetic radiation, its presence at the chemical reaction, it can increase the rate of reaction. Just you have seen in case of thermal energy, rate is increased when we are increasing temperature. So here also reaction rate may be increased, because it is particles of reactants, it is giving the particles of reactants more energy. Now how to understand whether this energy is high or low? It depends on the increase in intensity. That means number of photons. If it is very high for this electromagnetic radiation, that means rate of the reaction will increase. Okay, because now because of higher number of photons, the particles of starting material, it will also absorb more energy. Okay, so in this way, for photochemical reaction, particularly for photochemical reaction, radiation, that is what is the intensity of the radiation, depending on that, rate of the reaction may vary. Here we have an example of photosynthesis reaction. This is natural process. Carbon dioxide and water in presence of light energy. Light energy, it is expressed in this form H nu. The product that we are getting, glucose and oxygen. So this reaction basically it happens in presence of sunlight, which is a form of electromagnetic radiation. Okay, so this is the last factor on which rate of the reaction is dependent. Okay, so factors affecting rate of reaction, this part is complete. Next we will start integrated rate law. Now first it will be for zero order reaction, because that is the minimum order possible. Now what is integrated rate law? Because rate law we have already seen. Remember, rate law is like this: R equal to K, A to the power N. That is nth order reaction. R is rate, K is rate constant. So this is rate law. But what is integrated rate law? It is something different. So as we are saying integrated rate law, obviously we have to do integration. So these equations which are obtained by integrating differential rate laws. Okay, and why we are doing this? Because it gives direct relationship between the concentration of reactant and time. Okay, see here directly the relationship of rate with time you cannot see, right, in the normal rate law. But if it is integrated rate law, you can get direct relationship between the concentration of the starting material and time. So this is the utility of this integrated rate law. Fine. Now for zero order reaction, and remember one thing here, the process of integration in detail, that is derivation, that is actually not required, but I will show it because it is important as to know how we are obtaining this integrated rate. Okay, so in case you are interested, you can consider it. Okay, this is zero order reaction. Here we have starting material A and we are getting products. Now this integration that we will do basically on differential rate laws. Now this is actually differential rate laws. Okay, here n value is 0 and in place of rate, that is instead of R, now we have written minus dA dt. Why? Because with increase in time, concentration of starting material will decrease, so there is a negative sign, and this is equal to rate constant A to the power 0, because here order is 0, it is zero order reaction. Now anything to the power 0, it is always 1, so minus dA dt, that is simply equal to minus K. Sorry, if we have written minus here, so it is equal to K. Now if we are bringing dt term in the right hand side, it will be d concentration A minus k dt. Now we will do the integration both sides. So when we are talking about integration, there will be some limit. So initial time is 0, final time is t. When it is time 0, concentration of A is A naught. When it is time t, concentration of A is t. Now after integration and putting these two limits, we will get in the left hand side concentration of A at t minus concentration of A at 0, that is initial concentration. And in the right hand side, what we will get, K is constant, so it will not be considered in the integration. Only dt is there. So dt, if we do integration, it is simply t. And 0 to t, that means it will be t minus 1. Ultimately, the relationship that we are getting is concentration of A at time t minus concentration of A at time 0, that is equal to minus kt. And there will be a minus sign because initial concentration is always high compared to concentration at any time t. So that is why there is a negative sign. You can also write the equation in this way. Fine. So this is the final expression that we are getting. So a reaction is said to be zero order if its rate is independent of the concentration of the reactant. Because here, see, minus dA dt, this term is actually equal to K and K is constant. That means what? It is not dependent on the rate of reaction. Okay. And remember, unit of rate constant here is concentration multiplied by time inverse. Now concentration means moles per liter, that is molarity. And time, it may be second inverse, minute inverse, or it may be day also. Okay, hour inverse, day inverse, like this. So this is the unit for rate constant only for zero order reaction. So from the unit also you can understand, that is even no other information is given, just look at the unit, you will be able to understand that this is for zero order. Okay, fast concentration, that is moles per liter, and then it may be second inverse, minute inverse, like this. Fine. And zero order reaction, it is always multi-step reaction, and I have also discussed a problem related to this, that is zero order reactions, it cannot be elementary reaction because elementary reaction is only one step, and here rate is not dependent on the concentration of reactant. But if it is single step, it is not possible, right? So maybe in a multi-step reaction, suppose there are 3 steps and only one of the step is zero order, but overall order is not zero. It is zero with respect to a particular step among 3 to 4 steps. So that is why zero order reaction, it is always multi-step. Some examples of zero order reaction: photochemical reaction, that is electromagnetic radiation is used. Hydrogen, chlorine in gaseous condition, it is producing hydrochloric acid. And decomposition of N2O, which is one of the oxide of nitrogen, on hot platinum surface. And we are getting nitrogen and oxygen. So though here single steps are written, but do not think it is elementary reaction. It is not single step reaction, but this is the overall equation, because whenever we giving any example, we always write the overall reaction. Okay, that is the overall balanced reaction. We do not write the single steps. And the third one is iodination of acid. That is one of these hydrogen that will be replaced by iodine. So it is now ICH2COCH3, and one of this hydrogen, it will react with another iodine atom, it will produce H. So these are the examples of zero order reaction, and all of them must be multi-step. Is there any doubt? Should I repeat? Next, related to zero order reaction, what is the graphical representation? So this expression you have already seen, that is rate, that is ultimately equal to K, and K is nothing but constant. That means when you are drawing the plot of rate versus time, rate, see, there is no change in the value of rate because rate is not dependent on time. That is why the line is parallel to time axis, that is x-axis. Similarly, rate is also not dependent on the concentration of A. So when we have taken concentration of starting material in the x-axis, again you will be getting a line which is parallel to x-axis. Okay, so K is sorry, it is rate, not K. It is R. So rate is not dependent on time and even the concentration of starting material. Okay. Another graph. This expression you have already seen in the previous slide, and we have written this equation in this way because if you compare this equation with y equal to mx plus c, here c is basically a naught, that is intercept this value, the line where it is cutting this y-axis, this point and origin, this difference is basically intercept c, and here m is minus k because x is t, this is x. Okay, so as x is t, that means slope is equal to minus k, so it is negative slope. That is why the nature of the curve is like this. Fine. So when we are taking at in the y-axis, so this is basically y, right? Just compare these two equations, at versus time t. This type of this will be the nature of the graph. And finally we will see the half-life expression for zero order reaction. So from this equation you can also write this expression, that is K equal to initial concentration minus concentration at time t divided by t. Now what is half-life? Half-life means the time at which the amount of the starting material, it will be just half. That means 50% of starting material will be consumed and 50% will remain unreacted. It means that if t is the half-life, then at time t, concentration of A naught will be equal to concentration of AT, that will be equal to half of A naught because 50% will be remaining. Okay, So this is the concentration at time t. That means what is the amount that is left. So 50% of A naught is half of A naught. So that is why we have written in place of AT, now we have written half A naught. So A naught minus half A naught, this is also equal to half A naught. So ultimately what we are getting for this is T half. We are getting for T half, the expression is this. So remember, this is the T half expression only for zero order reaction, and here from this expression it is also clear that T half is basically proportional to A naught. That is, half life is proportional to the initial concentration, because the term in the numerator denominator, that is actually constant. Fine. So all these graphical representation for zero order reaction, is it fine? Should I repeat? Now for first order reaction. So when it is first order, obviously it will be now dependent, that is rate will be now dependent on the single reactant concentration. So remember the term R equal to K, A to the power N. Now the N value will be 1. That means it will be K, A to the power 1. Okay. So now rate, that is minus dA dt, same reaction we have taken. The differential law will be like this, K into A to the power 1. Instead of 0, now we have written 1. Now bring A in the denominator and bring dt in the right hand side. So why we are doing so? Because we have to do integration. So similar terms must be present on the same side. So now it is dA dt and this is minus k dt. Next, we have to do the integration. Here we have taken limits A naught to AT times 0 to t. So dA dt, after integration, it becomes ln A. Okay, and limits are there. So it will be ln AT minus ln A naught. And in the right hand side, it is just same as you have seen for zero order reaction, minus k into t minus 0. So it is minus kt. Now when there is a negative sign between 2 ln something, it becomes ln, that is, it becomes ratio. Okay, so if it is ln A minus ln AB, sorry, if it is ln A minus ln B, it will be ln A by B. So that is why it is written in this way. Now if we are changing the denominator and numerator, that is, if we are exchanging it, now the equation, it will be opposite. That is, if you are removing this negative sign, then in the right hand side also you have to bring a negative sign. So suppose I am bringing here a negative sign and also here. So ultimately it will be positive kft. Now anything before ln, that is actually the, it becomes the power of this. So this ratio will now have power minus 1. So now it will be opposite. And in place of ln, you can also write log e, because ln is basically, that is the base of log will be e. And when it is simply log, we write it is actually log, base is 10. But here it is exponential. But you don't have to think about it. You can simply write it as ln. So when we have written ln, it will change to ln A naught. Now I am writing A naught first, and in the denominator there is AT, and this is equal to KT. And if you want to write in terms of log, this equation will change to 2.303 log, because ln is equal to 2.303 log, and other expression as it is. Okay, so this expression you will see we will be using frequently. Okay, and if you are removing this ln term, now there is base e. So this is another form of first order reaction. That is also fine. That is AT by A naught e to the power minus kt. That means at is equal to a naught e to the power minus kt. So different types of expressions are there, all are actually same. You can take this log form, you can take this ln form, and these are the exponential form. So all these forms are basically only for first order reaction. Okay. We have some examples. Decomposition of H2O2 in aqueous medium, and from H2O2, that is hydrogen peroxide, we are getting water and oxygen. Then hydrolysis of ester. So here we have ester molecule, which is methyl acetate plus water. Though here two starting materials are there, but still it is first order because amount of water is so high that it is not dependent on the amount of H2, only on the amount of ester. And products are acid and alcohol. And the last example, inversion of cane sugar in presence of mineral acid. So the acid is not mentioned, but I'm writing it here as H plus. This is cane sugar, and ultimately we are getting this glucose. These are the products. Okay. So these three are examples of first order reaction. So is there any doubt? Now for zero order, we have seen graphical representation. Same thing we will also do for first order, but before that, just see how we can obtain the half-life expression. This equation you can recognize. Just remember in the previous slide, it is actually this equation. Just here the difference is k is, see, k is in the left hand side, t not, it is not kt because k is in the right hand side. Now when we are saying half-life, that means at will be equal to half of a naught. So that is why now in place of t we have written t half. In place of at we have written half of a naught. A naught will be cancelled. Ultimately it will be log 2. Okay. Now log 2 value is 0.3010. Multiply it with 2.303. So ultimately the value of t half, it is 0.693 divided by k. So a very interesting fact you can see here, in case of zero order reaction, we have seen that T half is directly proportional to the concentration of starting material. But in this expression, you will not see any starting material concentration. That means half-life for zero order reaction is independent of starting material concentration. It is simply 0.693 divided by rate constant. Okay, which is very important characteristic for first order reaction, that it is not dependent on reactant concentration. Here the expression is like this: rate is equal to rate constant into a to the power 1. That means it is k into a. Okay, now when we are saying rate, it is basically you can write it as dA by dt. Okay, so time is involved here. Now as if you are bringing this time in the right hand side, basically you will see that here r, that is rate, that is directly proportional to time. That means as we are increasing time, rate will also increase, and here slope is equal to a value. Okay, so this is rate versus time. In case of zero order reaction, what we have seen, that rate is when we have drawn the same graph for zero order reaction, then you have seen rate is not dependent on time. It is having a parallel line, which is parallel to x-axis, this type of line. But now with a positive slope, we can see here this is going through origin, and here it means that rate is directly proportional to time. Okay. Next plot is concentration versus time. As time is increased, concentration is basically decreased. Okay, you can also understand it from this expression, or you can simply take the expression that is AT A naught e to the power minus kt. So in the exponential, this is also for first order. Exponential, there is a negative sign before time, right? That means when you are drawing the graph by taking AT, that concentration of A at any time t, versus time, that is AT versus time, it will be exponential nature. So you can see from the graph, the line is not straight line, it is exponential in nature, because there is exponential term. T is present in the power of e, and there is a negative sign. That means when you are increasing time, the value of AT will decrease. So that is why the nature of the graph is like this. So suppose you have 0.1, this is 0.2. So obviously it is higher time compared to this. And if we just draw a line from these two positions, this is the concentration at position 1, and this is the concentration for position 2. You can see when time is less, concentration is high. When time is high, concentration is less. That means as we are increasing time, gradually the concentration of A will decrease. Okay, is it fine? And if you want to get explanation from this equation for this first graph, you can see. Okay, no, it is not possible because rate is not present. Okay, leave it. So is there any doubt? Next, what we are doing, same expression we have taken, right? Now bring 2.303 here and t here. Now it will be like this, that is kt divided by 2.303, and in the right hand side, now we are breaking this equation to log a naught minus log at. Now if you are bringing this term left hand side and this term in the right hand side, now it will be like this. Now it will be in the y-axis and t will be in the x. That means this is y, this is mx, and this part is intercept. So m is basically minus k by 2.303. So if you are drawing this graph, that is basically you are drawing the graph of log at versus time. This will be the nature of the graph. In the y-axis we have log at. In the x-axis we have time. And slope will be, see, this is the slope, minus k 2.303. But suppose if it is not log, if it is ln, then this 2.303 will not be present, then it will be simply minus k. So be very careful whether it is ln or it is log. That we have to be careful. So this is all about the graphical representation for first order reaction. In next class we will see what will be the general expression for nth order reaction, because order may have some higher values. So if we know the general expression for nth order, then we can derive any order. Just you have to put the value of it. So is there any doubt regarding the whole class? Okay, so we are ending the session here. Thank you for listening.